Well, welcome everybody to the most recent iteration of Office Hours. Hopefully, technical issues are mostly addressed at this point. Let me know if they're not. But today, what I really wanted to dive into primarily was the quite obviously present, making itself known, El Nino event in the tropical Pacific Ocean, the fact that it is continuing to strengthen and may further strengthen for months to come, becoming a pretty formidable event globally with a lot of not only global climate implications, but also regional climate implications for California and the western US. And I've held off talking about those for a while, simply because it's complicated and I wanted to see how El Nino was actually going to evolve along with the rest of the global oceans up till this point. But now that we're in September, we're nominally in autumn. I think it's starting to be time to have that conversation, and it's a conversation I'll revisit repeatedly in the weeks and months to come. So, El Nino, what is it? It's a temporary warming of the tropical eastern Pacific Ocean. Why is warming in this part of the Pacific Ocean so important? Well, it's part of a broader oscillation known as the El Nino Southern Oscillation. La Nina is the El Nino's cooler counterpart with cooler than average temperatures in the eastern tropical Pacific Ocean. But the reason why this is so important for global climate is La Nina events tend to sequester energy in the coupled Earth's ocean and atmospheric system. So if you look at them as sort of one whole system, as Earth scientists often do during La Nina events, there is excess heat stored in the ocean. And during El Nino events, a lot of that excess heat that was stored during La Nina events is liberated and enters the atmosphere. And so neither La Nina nor El Nino result in long-term changes in temperature, but they certainly do result in short-term accelerations or diminutions in temperature trends. So La Nina results in cooler global average temperatures for a year or so, and El Nino, of course, does the opposite with warmer than average temperatures every year or so. In the context of our rapidly warming climate due to global warming caused by the accumulation of greenhouse gases in the atmosphere, these El Nino events are kind of responsible for part of the seesaw warming effect that we see in the long term, where if you average over decades, the long-term warming trend is incontrovertible, but if you look only at a few years at a time, temperatures can either be flat warming or even slightly cooling, depending on whether we're in an El Nino or a La Nina cycle, superimposed on that long-term warming trend. So, of course, right now we're seeing a period of exceptional global warmth, record-shattering global warmth this past summer, in fact. All around the world, notably except for California, was one of the exceptions. But the interesting thing is that there has been just an unbelievable proliferation of record-shattering heat and also, and especially recently, record-shattering precipitation events. And I want to talk about both of those things today. Big picture, and then zoom into the more regional picture in California and the American West. So there is a real challenge when it comes to understanding the regional effects of El Nino because, of course, the regional teleconnections, so essentially the geographically remote effects of this tropical Pacific warming, are also dependent on what happens outside of the El Nino regions in California. And so excuse me there, sorry, I got a little bit distracted by the visual artifacts that are flashing more and more frequently on the screen. If anybody does have advice on that front, please do let me know. But what I wanted to say there is that the regional effects of El Nino, particularly in a place like California or the western US, is important not only, or depends not only on how warm the eastern tropical Pacific becomes as a result of El Nino directly, but also how warm or not warm other patches of ocean are concurrent with that tropical warming directly caused by El Nino events. And so what I mean by that is the North Pacific, for example, Gulf of Alaska, is it much warmer or cooler than average concurrent with that El Nino warming in the tropics? And right now, many of the global ocean basins are experiencing record warmth. not just El Nino related regions, but regions that have no known connection directly to El Nino. So there might be other multi-decadal oscillations at play in some cases. What the big picture really does appear to be the long-term warming of the oceans is really it is really manifesting itself in pretty dramatic form this year on top of El Nino. So there are patches of ocean near Japan, in the Gulf of Alaska, all throughout the northern Atlantic, all the way from the eastern, the Atlantic coast of Canada to parts of the central North Atlantic, extending all the way east to the Azores Islands. So that's a huge extent of record warmth in the oceans that is not directly related to El Nino, but is going to affect how El Nino brings regional climate impacts. So that regional warmth is important because it changes, and in many cases reduces, the ocean temperature, the anomalous ocean temperature differential. So the main mechanism by which El Nino drives regional changes in climate when it occurs, particularly during strong events, is to shift the latitude at which these big tropical thunderstorm clouds that reach to very high levels in the atmosphere occur. In a typical condition, or a La Nina condition, those tall tropical thunderstorms are mainly constrained to the tropical West Pacific Ocean. So way on the other side of the Pacific Ocean from South America and North America, closer to Oceania and Southeast Asia. That is the part of the Pacific where most of these tall tropical thunderstorms occur most of the time, because the ocean there tends to be warm enough to support that level of, it's called deep convection, tall tropical thunderstorm clouds. And the prevalence of those tall tropical thunderstorm clouds in the western Pacific Ocean tends to induce certain changes in the jet stream, even in geographically remote regions thousands of miles away. And so the difference is, during El Nino, you have warmer tropical ocean conditions extending farther east into the Pacific Basin. So depending on the El Nino event in question, that might be the central Pacific Basin during El Nino Modoki, as it is called, those central Pacific El Ninos, or during a more east-centered event, as the present one appears to be, with the maximum anomalous warming occurring pretty close to the coast of South America, so west of Peru. The longitude, so essentially the section of the tropical Pacific that sees the most anomalous warming, tends to be the section of the Pacific that sees its relocation of tall tropical thunderstorms. So instead of occurring preferentially in the tropical western Pacific Ocean, they occur either over the central Pacific or even sometimes over the eastern Pacific. And the reason why that matters is because the waves in the jet stream that these tall tropical thunderstorm clouds can induce shift their position, depending on where longitudinally the preferred region of tropical convection is. So essentially what matters is the gradients, the horizontal gradients in temperature, or temperature differentials, if you will. And so you can imagine, if the equatorial Pacific is drastically warmer than average, but the North Pacific Ocean is relatively close to average, then you're going to accentuate, you're essentially going to increase the difference between the tropical ocean and the mid-latitude ocean temperature-wise from what it would normally be. So if the mid-latitude ocean stays the same, but the place that's already warmer, the tropics, gets even warmer relative to the mid-latitudes, well, then you've increased that temperature differential from in a latitudinal sense. But the opposite can happen if you have warming of the tropical Pacific Ocean, but you also have warming of the extratropical Pacific Ocean. So if the tropics warm by 2 or 3 degrees, as looks like it could potentially occur during this El Nino event, and the mid-latitude oceans also warm by 2 or 3 degrees, as they already have recently, and it looks like that's going to persist for some months, then we actually have a situation where it's not so clear whether that differential has actually changed. El Nino is clearly there, it might be very strong, global warming is clearly there, it's warming the oceans in other places as well, but is El Nino going to have the typical, canonical, expected effect? Because we've altered the temperature differentials in the ocean, which can affect the position or the magnitude of the enhancement of the jet stream that we often associate with El Nino events, which is what can bring increased precipitation to the Pacific Southwest. We tend to see during a classical moderate to strong El Nino event an enhancement of the subtropical portion of the jet just to the west and south of California that tends to drive more active storms into the central and southern parts of the state and into the interior Southwest during winter. That is the canonical view of El Nino. It's associated with an unusually deep Aleutian low and an unusually strong and southeastward shifted jet stream that tends to direct more winter storms towards California and the Southwest. The question is, during this event, will it happen? And the answer is, well, it depends. So let's break that down a little bit. First, we know that this El Nino event is likely to be a strong to very strong event. In fact, some of the best predictive models are still suggesting it could become among the strongest ever observed in terms of the magnitude of the ocean surface temperature anomaly in the El Nino region. It could reach between 2 and 3 degrees centigrade. That's a very, very large anomaly for the El Nino region. And right up there with the strongest ones we've ever observed. So we check that box. Moderate to strong El Nino, very likely yes, this winter. Possibly very strong, perhaps only moderately strong, but it's definitely not going to be a weak event because we're sort of already there. Number two, we're thinking about what we're thinking about the potential for these unusual ocean temperature gradients because of all this pretty extraordinary and record-breaking ocean warmth in other regions outside of the tropics to potentially affect that typical El Nino connection. So we check that uncertainty box as well. Is this event going to be an east-based event versus a central basin event? It does look like this one is going to be a little more east-based than the last big El Nino event we saw, and so the answer seems to be yes to that as well. So we check the box. Will it be strong? Very likely yes. Will it be east-based? Probably so. Those are the two boxes we normally need to check to have the greatest effects in California and the Southwest during winter. But then we also have this other box checked, the complicating factor of the unusually warm non-tropical Pacific Ocean as well. So what do we do with that information? Well, proceed with caution, because it means that even though the tropical thunderstorm activity probably will be centered pretty far east in the basin, and that will result in a pretty substantial enhancement of the subtropical jet stream in the eastern Pacific Ocean, will it occur at exactly the right longitude and latitude to bring wet conditions to California and the Southwest this winter? And that is where the anomalous warmth of the extratropical Pacific Ocean comes into play. It might affect, in somewhat subtle ways, exactly where is that Rossby wave train, which is what it's called when you have these large-scale wave-like perturbations that emanate from the tropics and have the greatest effects in the mid-latitudes where the Coriolis force is stronger. Will the unusually warm non-tropical oceans essentially mess up what otherwise would be a pretty classic strong El Nino response? Well, the most honest answer is I don't know, but I think what's probably most likely going to happen at this point, based on both sort of first principles physics, understanding how historical events have developed, albeit under different conditions, because we've never observed a combination of a very strong El Nino event plus record warm non-tropical oceans simultaneously before. So there is no observed analog for what we have going on this year. And then also look at the dynamical predictive models that we have, because those should at least ostensibly be able to take into account both of these factors at once. And they're not perfect models, and there's lots of uncertainty, and we need to take these predictions for what they are, which is probabilistic rather than deterministic, meaning that they can give us hints as to tilts in the odds, but they can't actually give us an answer as to definitively whether it will be wetter or drier than average in a particular place. but it can tell us something about the odds that a season will be wetter or drier in a particular place. What are those telling us right now? So a combination of my personal physical intuition based on the field that I'm in and these dynamical models, what do they tell us about what's coming up? Well, let's start with the dynamical models because that's probably the easiest, most objective thing to talk about. They are suggesting a relatively classic El Nino response, where Central and Southern California experience wetter than average conditions during winter, particularly during the second half of winter, so particularly January through March, which in Southern California do tend to be the wettest months of the year anyway, and to a lesser extent maybe December, although it's a little bit more of a wild card. It's important to remember that El Nino does not necessarily bring wetter conditions in autumn. So it may slightly increase the likelihood of tropical storm remnants reaching California, and we've already seen a pretty dramatic example of that this year, where an actual tropical storm, Hillary, reached California last month. That probably had at least something to do with El Nino. But could it happen again in the next 2 months? Yes, there's a possibility. A little bit of tropical moisture might make it towards Central California, actually, in the Southern Sierra a little bit later this week, although it won't be a significant event. Certainly not on the order of what I'm talking about here. But unless that happens, it's actually, there's a slight tilt in the odds towards drier conditions this autumn in California, particularly in the north. Of course, the wild card being if there's a single tropical storm remnant event again, then that would completely skew the seasonal total in the wet direction. So wouldn't say take that with a grain of salt, but in California, El Nino doesn't really give a strong predictive signal for autumn precipitation, except that it may slightly increase the likelihood of tropical remnant events, but it slightly decreases the likelihood of all other types of precipitation. So unless we get that tropical remnant event, we could actually have a pretty dry and relatively warm autumn, especially because ocean conditions are now warmer than average up and down the California coast. There is a stronger signal up in the Pacific Northwest and British Columbia, unfortunately, for a dry autumn, which is not what they really want to hear up there right now, because this has turned into a rather severe fire season in some places, particularly in British Columbia on the Canadian side of the border, and really all throughout Western Canada. The fire season in Canada, and I actually think it's worth having a separate office hour just on the Canadian wildfires this year, because they are so exceptional and they continue to be really mind-boggling amount of area burned at high intensity and just an unbelievable amount of carbon emitted into the atmosphere. But the point here is that unusually dry conditions are likely to persist this autumn, possibly warmer than average conditions as well in the Pacific Northwest and in British Columbia, and that's not good news because drought is rapidly developing in these areas, and the wildfire season in some spots, particularly north of the border, has been exceptionally or historically severe. So that's not great news this autumn up there. In California, this might be more concerning had we not come into this autumn with a bonus summer rain event in Southern California associated with Hillary, which really made things quite wet. And also, at least in the higher elevations of Northern California, things are still relatively damp as the legacy both of the wet winter we had last season, the cool spring, and then again a more recent precipitation event just a week or so ago. So I'll come back to what autumn fire season might hold for California later in this call. But for El Nino autumn teleconnections, not much to say for California except for that sort of nuanced picture. Could go either way. If we get above average precipitation, it's probably because we get another tropical remnant event. Otherwise, likely to be lower than average. But then winter, things change pretty dramatically. Well, at least for California. Unfortunately, in the Pacific Northwest and British Columbia, there's a pretty strong indication that this winter could be drier than average. Again, not what folks want to hear up there. Of course, drier than average up there still probably means that fire season ends because you take British Columbia's average precipitation and divide it in two, and that's still enough precipitation to hopefully really shut down fire season by late autumn, early winter. But still, any delay in fire season up there to the end of fire season up there is not good news. And if it's a dry winter, that really sets the stage for what might then unfold next spring and summer up there, following what was already a terrible fire season up there this year, along with potential water availability concerns associated with drought. So that's sort of what we're thinking about right now, Pacific Northwest and British Columbia. But in California, this winter, there are stronger signals than for autumn in terms of precipitation, which is to say, if I had to make a guess right now, I would essentially lean moderately towards wetter than average conditions for central and southern California in particular. If we get lucky, that those above average conditions could extend all the way up to northern California and encompass most of the winter. But this highest confidence statement is really for central and southern California during the second half of winter, so January through March, where it is more likely than not to be wetter than average. Now, how much wetter than average kind of matters a lot this year because we had a wet winter last year. There is still water in the Tulare Lake bed. This summer, we saw pretty exceptional precipitation in some parts of southern California, including the deserts, which saw a year or more's worth of precipitation in places like Death Valley in just a day or two, associated with Hillary, with severe flooding. So the deserts have seen a lot of water already this year with pretty transformative flood events. There still are soils that are moister than usual, certainly not as dry as they usually are, at high elevations in the Sierra Nevada, which has helped greatly with fire season this year. There hasn't been much of a fire season up in the High Sierra because of it this year. But what it means is that the soils are going to go into this coming winter with some moisture already in them. They aren't completely parched. So that's great for ecosystems right now, but it might set the stage for it to be easier for there to be flood concerns that emerge sooner than they would have if we were going into this strong El Nino event coming out of a drought. So this is something we're going to have to watch for closely. One additional consideration, and now this is me speculating a little bit more. This is that general prediction is based off of the dynamical models. I think that there is reasonable evidence just based on the way El Nino events, strong ones unfold, east-based events unfold, and what the dynamical models are telling us. Tilting the odds towards a wetter than average winter in central and southern California at least, and for parts of the interior southwest, and then a drier than average winter up in the Pacific Northwest and British Columbia. That's what it looks like right now. What are the odds of either that forecast being wrong and it not being wetter than average, first of all, or that tilting the odd towards wetter than average conditions being a dramatic understatement and seeing just a complete inundation and widespread flooding in California this winter? So two ways that tilting the odds towards wetter than average conditions could either be an over or an understatement. So what are the odds of those predictive failures occurring? Well, I'll say at the outset that either could occur, but there's a couple of reasons why I'm thinking that this is somewhat more likely than usual to be a dramatic winter in one respect or another in California. The reason for that is, so I was talking earlier about how the temperature differentials in the Pacific between the tropics and the mid-latitude regions can interfere with the typical El Nino teleconnection and the ability of El Nino to bring above average precipitation to parts of the Southwest during winter. And that is at play, and it may affect exactly where the jet stream sets up, and it may not be fully favorable for California. It could be that the jet maximum is a little bit too far west or too far east. Sometimes there can be a gap near California, and California doesn't take as much of advantage of this enhancement of the storm track. But the other possibility is that the jet stream does do what we would expect it to do during a strong east-based El Nino event, and sort of slams right into southern and central California repeatedly between January and March in particular. And because the northern Pacific Ocean, so the non-tropical part of the Pacific, is warmer than average, if there are storms that develop over that part of the ocean and move over California because of an El Nino enhanced jet stream, they would be potentially containing even more moisture than usual for an El Nino event, because the extratropical or the mid-latitude oceans are contributing additional moisture beyond what they normally would. And what we know from recent research about atmospheric river storms is that a large fraction, the majority usually, of the actual water molecules in atmospheric rivers that eventually fall out as precipitation in places like California, they don't come from thousands of miles away. So we think about this sometimes as there being a huge transport of individual water vapor molecules from the tropics. And there are some that do make it here all the way from the Hawaiian Islands, but it tends to be a minority of the actual water vapor is being physically transported directly from thousands of miles away and falling on your head in California. Instead, what's happening is this constant corridor of precipitation and condensation and re-evaporation going on in the atmospheric river axis. And so most of the water molecules that end up falling, most of the moisture that ends up becoming precipitation in California, is only coming from the ocean, evaporating from the ocean within a few hundred miles of California. So what does that mean? Well, it means if the ocean within a few hundred miles or 1,000 miles of California is warmer than usual, then the storms that do make it over that region might be juiced up even more than they would be otherwise. So now we have two things to contend with. We have the direct effect of a strong east-based El Nino event, which is affecting usually not so much the amount of moisture that's available for storms in California, but is affecting the storm track itself. So the primary reason why El Nino events are associated with increased precipitation across the southwest, subject to all of the caveats I just mentioned, is because it enhances the jet stream and increases the propensity for winter storms to make landfall directly in California rather than giving California a glancing blow. The subtropical jet enhancement is the reason why this connection is stronger for central and southern California than it is for the northernmost parts of California, because this really is a subtropical jet stream enhancement. If you're up in Eureka, you're not really in the subtropics, but if you're in San Diego, you're essentially in the subtropics. So that's partly a function of how different California climate is from north to south. But the thing is, if you have that enhancement of the dynamical aspects, so the storm track, the jet stream, the Aleutian low, and you combine it with additional moisture in the form of that stems from warmer than average water in the non-tropical ocean within 1,000 miles or so of California, as we currently have and is expected to continue now for several months, that's a recipe for some pretty intense storms and some very moist atmospheric river events in California and other parts of the Southwest. So the challenge is really what is going to happen with this unusual combination of a very strong, potentially El Nino event in the eastern tropical Pacific and record warm conditions not only in the North Pacific Basin but also elsewhere in the Atlantic. Will that mess up these teleconnections? Because if it doesn't mess up the teleconnections, it might actually further increase the likelihood of very or exceptionally wet conditions in California, because El Nino is enhancing the jet stream and the storm track, and the warm non-tropical ocean is just adding more fuel to the fire, if you will, or more moisture to the atmosphere that can be leveraged by those enhanced storms. But if those extratropical oceans are essentially acting to offset the storm track enhancement, they're going to pump more moisture into the atmosphere, but there may not be enough storms to take advantage of it and bring that enhancement of precipitation. And we see this, there's a little bit of divergence in the dynamical models, where the American model and some of the other seasonal predictive models essentially show a pretty wet winter, especially January through March period for California, so significantly wetter than average for most or all of California. But the European model is not quite so wet, or has more individual members within its ensemble that are neutral or even drier than average in California this winter. Why is that? Well, there's always a range of natural variability. We've seen that with the last big El Nino event in 2015, 2016, which was not an exceptionally wet year in California, which, as I've talked about before, I think folks have overblown the degree to which that changes our priors about El Nino. I don't think it really does, but it does illustrate that El Nino is not the only game in town. The thing is, this year we know that there is specifically another game in town. So we're not hypothesizing that there may be a competing influence. We're pretty sure there is. But the question is, it's simultaneously a competing influence from an atmospheric dynamics perspective, but an aggravating influence from an atmospheric thermodynamics perspective. So it may screw up the storm track, but it might enhance those storms that do make it through. Which factor wins out is probably going to dictate what happens this winter in California. So it's still early. It's early September. We have a few months. The autumn looks rough in the Pacific Northwest and British Columbia from a drought and fire perspective. The autumn does not look so rough for California because it doesn't look like there's a strong signal towards much of anything. It looks relatively mild. I think this is... I'll get into fire season just in a moment, briefly. But I did want to point out that this El Nino event is occurring in the context of global temperatures we've never seen before, and so it's going to be scientifically interesting, but also a little bit nerve-wracking from a hazard and planning perspective, because we don't know exactly what's going to happen. And these are not unknowable things. These are not necessarily things that can't be captured in seasonal predictions. So when we're talking about these dynamical model predictions, those should be incorporating these disparate, potentially competing factors. Maybe not perfectly, but it's not like these models are not capable. The dynamical coupled ocean-atmosphere models, they know that the extratropical oceans are warmer than they ever have been before in the context of a strong El Nino event. So that's not information that's missing. The question is, are these models interpreting that correctly and doing the thing that the atmosphere and the oceans are actually going to do this winter? Which is, of course, always the question in climate science and meteorology. Are the models doing the right things for the right reasons? And I think we can cautiously rely on them in the affirmative, but it's definitely a trust but verify situation. And even if you look carefully at the ensembles, you see that there is a conspicuously wide range of outcomes, even for the same models getting approximately the same initial conditions. So that's the beauty of ensemble modeling, where we run the same model over and over again with ever so slightly different initial conditions to see the range of possible outcomes. In this case, it's pretty sensitive to those initial conditions, and so that suggests that there is a pretty wide range of potential outcomes, and for all the reasons I was just talking about, I think that's why. Just give me a water break for a moment here. All right, so that's mainly what I wanted to say about El Nino for now. I'll talk more about it later. I will also answer questions about it at the end, but I do want to move on to other things now. The onslaught of extraordinary extreme weather in the Northern Hemisphere, and really in the Southern Hemisphere as well, we just haven't heard about it as much as we often don't, continues. It has been just a bewilderingly extreme summer from a temperature, heat extreme perspective, from a flood extreme perspective, and from a wildfire perspective in certain regions. This year has been the year of just mind-boggling Canadian boreal forest fires and record-breaking and catastrophic fires in the southern Mediterranean region specifically. Those have really been the hotspots this year. For heat extremes, it's essentially been everywhere. Parts of the US, Canada, Europe, Asia, Africa, even Australia and South America, which of course are in the other hemisphere, and where it has been winter, they too have been experiencing record warmth. So man, it has really just been occurring everywhere. Numerous cities and countries have set their all-time hottest temperatures on record this year. So records that have stood for hundreds of years in some cases have gone by the wayside in droves. So this has been a searingly hot summer in most places in the Northern Hemisphere. Again, ironically, except for California and some adjacent regions where it has been a comparatively mild summer, although it is worth pointing out that even this relatively mild July and August in most of California ended up warmer than the 20th century average still. It's just that it felt cooler relative to recent years because it was. But recent years have been so far above the 20th century typical values for summer, I think we've gotten a bit inured to it. But thinking outside of California, I really wanted to mention a couple of things that have just unfolded and literally over the hours leading up to this live stream I've just been following. It's gotten a little harder to follow with the state of social media right now. But from what I can tell, three big things have just happened. One is that some of the largest wildfires ever recorded in Europe over the past couple of weeks unfolded in Greece. Unfortunately, there was significant mortality and significant loss of structures. These were high-intensity fires that occurred amid record high temperatures and severe drought. Well, in the past 72 hours or so, parts of Greece have experienced an extraordinarily record-shatteringly, and again, I don't use record-shattering casually. I mean, record-shattering in my book means you didn't just break the record by a little bit. You took the previous record and you just exceeded it by an enormous climatologically remarkable margin. So when I say that all of these things are record-shattering, that's saying a lot. This is, I think, in many ways, Greece's arc storm-like event. For those of you who have followed my work on the increasing risk of an extremely severe flood event in California in a warming climate, I think Greece has been essentially witnessing an event of that on that magnitude over the past several days. And it is ongoing. It is not over yet, but widespread catastrophic flooding is now occurring throughout large portions of Greece. There's dramatic videos of huge flash floods sweeping through the streets of Athens and washing tourists out of restaurants, among other horrifying videos. But that's just what's happening in the big cities. What's happening further inland in some of the river valleys is even more astonishing, where floodwaters have reached the second story of buildings and in some cases are still rising. These are really shocking values. This was predicted correctly by models in advance. There was some skepticism in the meteorological community that the models were suggesting that over the course of 2 or 3 days that a meter or more of rain could fall. So that's, for those keeping score, that's about 36 to 40 inches of rain over a few days in a place that is not accustomed to it, although at that point there are very few places that are accustomed to that much water in that little amount of time. And of course, this is all occurring just days after essentially the largest wildfire in European history occurred in almost the same part of the continent, within Greece. And there is overlap between the severe flood region and the record fire region within just a few days of each other. Extreme record-breaking heat also, just not so long ago, just a week ago, in the same places now experiencing rainfall that greatly exceeds anything on record in this part of the world. And the floods are catastrophic. I am sure that the floods in the fire zone are even worse. I haven't even really heard any details about this because it's been difficult to get information. But I just want to highlight the remarkable transition between record-shattering heat, the largest and deadliest wildfires on record in Greek and potentially European history, and then immediately followed by what is now probably the worst flood event on record in the same places. Certainly the most extreme precipitation event on record in a lot of these places. Other parts of Southern Europe have been similarly hard hit. There were more regionalized catastrophic floods in Spain and other parts of Southern Europe in recent days. The culprit is, well, once again, a stuck weather pattern with a classic omega-type atmospheric block. Omega being literally because if you look at high pressure, if you look at a surface pressure or an elevated geopotential height map, looks like the Greek letter omega. In this case, the center of the omega is literally over Greek, which is a bit ironic. But what is essentially, or it used to be, the center of the omega, which is where the high pressure is, was over Greece last week, but now this whole system has shifted. And so now Greece, where it's seeing extreme precipitation, is on the back side. So in the sort of in the persistent trough region, where there is a great deal of cyclonic storm activity occurring. Now what's happening as this occurs is that something called a medicane, sort of a composite word for Mediterranean hurricane-like storm, now appears to be forming over the region. And this is facilitated by Mediterranean sea temperatures that are at record warm levels. Now, there have been medicanes before, Mediterranean tropical-like cyclones. They're called tropical-like because they are still a little bit different than true hurricanes in the sense that they tend to have a slightly lower ceiling on their maximum wind intensity because the Mediterranean basin is just geographically smaller And the warmth of the ocean there is usually just nominally warm enough, although right now it's significantly warmer than that. But the problem with these metacanes is usually not the winds. They can produce some damage, but usually it's tropical storm, Category 1 type hurricane wind damage. But what they can produce is just extraordinarily torrential downpours because they tend to flux enormous amounts of subtropical moisture drawn from the warm Mediterranean into the mountainous terrain of Greece or Italy or any number of places in southern Europe that can be susceptible to them. And I don't believe that this was even what happened in Greece in this case. This was the precursor to the storm that brought this record-shattering precipitation event to Greece. But now they may see even more torrential rain as this Medicane-like, tropical-like storm feature develops. So simultaneously, other regions on the other side of the block, or at the middle of the block, if you will, are experiencing record warmth. So these persistent weather patterns, these stuck horseshoe-like perturbations in the jet stream, the omega block, you kind of call it like the Greek letter omega or like a horseshoe. They kind of a similar visual imagery there. The point being that there's a really big honkin' high-pressure system at the middle of the block, and usually there's a pair of persistent low-pressure systems on either side with the high pressure in the middle. And so you can get extreme heat, record-breaking heat, wildfires, all that stuff in the middle, and you can get persistent bouts of extreme precipitation and floods waiting in the wings. And these blocks can shift around a bit, but they tend to be persistent, and this one has been very persistent. There's some evidence that we're seeing more of these persistent weather features, particularly in the northern hemisphere summer months, due to changes in certain aspects of the jet stream. It's still a little bit speculative, but the evidence of that does continue to pile up. So it's one of those things that gives us pause, because that might help explain why we've seen so many extraordinary extreme heat and precipitation events, not only in Europe, but more broadly in recent summers across much of the northern hemisphere. There's a lot of work still to be done on that front, but I think this is just yet another example of what can happen when these things set up. It's not the only thing that's going on, of course, but right now in Greece and southern Europe, this is the big story, and it is a big story. And I think there's a lot of untold, pretty dramatic flood imagery to come out of Greece than we've seen so far. And I just wanted to bring up that something similar is going on now in parts of China. And I believe that just before logging into this, I was seeing videos from Shenzhen and then also from Hong Kong of just enormous flash flooding in highly populated urban areas, with subway tunnels filling up, people frantically trying to get out of underground garages, cars and vehicles washing down the street at the level of the top of the first floor of the buildings. Similar imagery out of Spain and Greece in recent days. Again, that's a lot all at once. And there are connections, of course, to a warming climate and extreme warmth. Extreme warmth begets more extreme precipitation. As the climate warms, we see a higher and higher ceiling on the potential intensity of precipitation. It doesn't mean it rains more all the time everywhere, but when it rains, increasingly, it pours. And boy, is it pouring right now in Greece and China and any number of other locations that have seen severe flooding this past summer. Again, as I said before, if this were a fluke, if this were inconsistent with recent years, then that might be one thing. But this is really just a further escalation beyond what we've seen, similarly shocking imagery in recent years in other places. So it's a bit of a sobering moment, I think, just to see the impacts of a year that's temporarily gotten us close to 1.5 C of warming. We're not at the 1.5 C of global warming long-term value yet, because we'll probably see a couple of years that aren't this warm, between now and 2030. But the reality is, this is sort of giving us a preview of what it's going to look like all the time at 1.5 degrees C of global warming. And so what does it mean then to get to 2 degrees centigrade of global warming, or 2.5 degrees of global warming, as we're still on a path toward? I reflect on that constantly as a climate scientist who studies extreme weather events. It's not fun to see these unfold, as somebody who really understands both the causes and the consequences of them. But I think, one of the things we do in these sessions is bear witness to some of them. So I don't want to talk too much more about the Mediterranean. I want to remark, since this is already running a little bit long, and I do want to answer some questions at the end. I do also want to touch briefly on fire season in California, since I know folks are asking. It has been a mild fire season almost everywhere except for the northwestern corner of the state, where it has been quite a severe fire season. And not as many people live up there in that corner of the state, so I want to make sure it's not forgotten. It has calmed down a bit in recent days since I did get some rain up there, which has helped. Given the fuel types, these are very dense forest fires, mainly in that region. I don't think that the rain we've seen has extinguished them, so those crews are going to be up there for a while longer. And if it dries out, warms up, and gets windy, those fires up in northwestern California could very much spring back to life, because we did not have the kind of super wet winter up there that we did in other parts of the state. And it actually has been warmer than average for quite a good chunk of the summer up there as well. So I don't think that we're totally out of the woods up there in the northwestern corner of the state, but it is looking better, at least right now, than it was this time last week, because they did get some rain over the weekend up there. What about the rest of the what about the rest of the state and the rest of the season? Sort of as this season has gone, largely according to early predictions, that it would be probably a somewhat milder than average fire season overall. There would be not much of a fire season to speak of at high elevations due to essentially the antecedent wetness and coolness. That part especially has played out well. We kind of defuse Southern California's fire season and fire season in some parts of the Southern Sierra further by this deluge from Tropical Storm Hillary. So that sort of cut things off right as things were starting to get hotter and drier down there. The one part of the state that hasn't really seen major precipitation, out-of-season precipitation this summer is Central California and parts of the Coast Ranges. So there are patches of Northern California that have seen significant precipitation over the past 2 or 3 weeks, and there are other parts of Central and Northern California that have seen almost none, just sprinkles at most. So there is a bit of a patchwork of fuel moisture right now. On average, fuel moisture is at or higher than average levels right now, meaning that the vegetation is either as moist as it would have been typically at this time of year, 20th century, or even slightly moister than it would be typically at this time of year, which is good, because it means that the fires that do occur are going to be generally less aggressive, less dangerous, and potentially more on the beneficial side of things, depending on where and when they occur. Maybe it might mean that there's some opportunities to do some prescribed fire, put some good fire on the ground more at the higher elevations later into the autumn than we've been able to do in some recent years during very dry, windy autumns. Especially at the higher elevations where fire season never really emerged significantly this year. At lower elevations, though, even though we've seen a break, there's not a lot of fire activity right now. There's also no immediate prospect for things to get damp again. In fact, the next 2 weeks or 3 weeks in California generally look quite dry and a little bit warmer than average, so things are going to dry out again. And if we get offshore wind events this autumn, none are in the cards right now, but if they occur later in September, October, or November, and we don't get another significant rain event between now and then fire season could reemerge. And, I just want to highlight to folks that in places like the Bay Area and the lower foothills ringing the Sacramento Valley, there's no reason why there couldn't be an episode of extreme fire weather again if we get a big wind event before the first big rain event of the season in these places. So fire season so far has been mercifully mild outside of northwestern corner of California, where it has been pretty bad as of late. But in general, this has been a reprieve year in California, largely as predicted. That was pretty much the outlook for the season, and it has largely borne out. I just want to caution folks that don't let your guard down if you're in the lower foothills or in the Coast Ranges or the Bay Area, because if we do get big wind events this fall, there has not yet been a season-ending or even a majorly season attenuating event in those areas yet. So fire season, good news largely so far, but it remains to be seen what happens between now and the end of November. Of course, the picture is completely different up in Pacific Northwest and especially Canada, where things are just completely off the rails, bonkers, insane fire season. Everyone I've talked to up in Canada has completely lost superlatives. It's almost like taking what occurred in California in 2020 and how anomalous that felt relative to the decades before it, and then multiplying it by a factor of 2 or 3. Really, that's the degree to which the Canadian fire season has gone nuts this year. So anyway, that's what I wanted to say about fires, or lack thereof, as the case may be in California. And I think I covered all the main topics I wanted to right in time for the end of the hour, but so this one will run a little bit long because I spent some time droning on about technical issues. So I'm going to go through and answer questions now. There's not too many of them, so I think I'll be able to get through a lot of them. Just for those who are still on, just a favor to ask. I did want to query people. I actually have not noticed interruptions to the stream this time for the first time in a few months. So in terms of, I have seen these visual artifacts, these blips that I need to figure out, but that I don't think is an internet connectivity problem. That is something about the camera or the connection between the camera and the software. So separate issue, ignoring that for a moment, although if you know how to fix it, please do tell me, send me an email. But I want to just verify that folks have not seen connection drops where there's the spinny wheel, or where it seems like I've suddenly jumped from one word to another word in non sequitur form. I haven't detected that, so this could be good news. It could suggest that finally this router is the one that seems to have contiguous upload, even though our ISP has not changed or done anything to help out. All right, well, so far, looks like good news. So I will take the visual artifact problem over the streaming problem. It is probably easier to troubleshoot, although, again, if anyone knows how to do it, let me know. The answer may be I need to buy yet another new piece of hardware, a new camera, or potentially replace the hub through which the camera connects to the computer. It's possible that's an easier fix. So just let me know if you have advice. All right, let me go through questions here. Hello, everybody. Lots of people saying hi in the beginning. Some volume stuff. Yeah, again, I'll fix the echoes. That I can deal with. I just need to put some sound baffling up in the room. Still some smooth edges in the room, and it's probably causing some background echo. Let's see. A lot of comments on the tech side. Thank you for that. Let's see. So I answered a few of these comments. Maybe this is a case where I've answered most of the comments in the course of an almost hour-long monologue. We'll see. A question from Anthony Edwards about whether the confidence is higher regarding Sierra Nevada impacts from El Nino, sort of the rain-snow line, versus a coastal California. I actually would say the opposite is probably true. Usually there's a stronger relationship between El Nino and winter precipitation along the central and south coast of California than there is across the north coast and the interior of California. This year, we have a strong enough El Nino that I think even the central and southern Sierra will probably get in on the increased precipitation. But there is the interesting question then of temperature, and then what happens to the rain-snow line in the mountains. So is it rain falling at high elevations, or is it snow? This is a tricky one because El Nino does two things. Dynamically, what it does is it actually tends to result in a pattern where you have cooler temperatures because you don't have as many clear, dry days in between storms. But on the other hand, it does tend to result in storms that are somewhat warmer than their counterparts otherwise because they're sort of enhanced by the subtropical jet stream. Does not necessarily mean these are super warm Pineapple Express types atmospheric rivers in all cases. In fact, some El Nino years we just get this constant west to east onslaught with a fair number of pretty cold storms. But I do think this is a case where El Nino is probably going to interact with the long-term warming trend. This is a year where I would not necessarily expect to see the kinds of exceptionally cold precipitation events that we saw last winter in some cases that brought these unbelievable snowfalls. So, 12,000 feet, sure, there'll probably be some unbelievable snowfalls in the southern Sierra this winter. But I think that the foothills, Lake Tahoe level, are less likely to see those extremely epic snow amounts just because it probably will be harder to get those extremely cold storms. Could there be some cold storms? Sure. But overall, given how warm I think this is less a function of El Nino and more a function of how warm the North Pacific is going to be this year. I think it's going to be harder for that zonal flow, that west to east flow, to bring in super cold air simultaneously with enough precipitation to cause those huge lower elevation snowstorms. So there could be some huge snow totals at very high elevations, but I do think it's likely to be a much higher rain-snow line on average than last winter, even if we do see above average precipitation in the southern and central Sierra. That actually is a distinct possibility, but it's probably going to pose potentially more upfront flood risks because more of it may fall as rain rather than snow. That's going out a little bit on a limb, but this is the kind of winter to look out for that because we have not only El Nino to juice up the storm track and the jet stream, but we also have a very warm non-tropical, extratropical Pacific to juice up the storms and warm up the atmosphere by a degree or two as well. And sometimes a degree or two is all it takes to push you onto the wet side of the rain-snow line, as a lot of folks in South Lake Tahoe are all too accustomed to over the past decade. Last year accepted. Jim W. 360 remarks that a certain location in Greece got 21 inches of rain in 10 hours. I don't personally have a way to verify that, but given what we're seeing, that is possible in some mountainous area that got hit by a training convective cell. That is the level of precipitation we're talking about. And just to be clear, earlier today, I guess it may have been yesterday now, technically in China, but in Hong Kong, parts of the city saw 6 inches of rain in 1 hour. 6 inches in 1 hour. I think there are years where LA has seen less rain than that. And, this is a highly urbanized setting. Of course, all that water's got to go somewhere. Even just, half a foot of water on the ground, even if it were just the instantaneous amount of water volume falling directly from the sky in a given place, that would be hard to manage in an urban setting. But of course, you have runoff and drainage. All that water accumulates, then in lower areas it flows downhill, and it becomes much more than 6 inches in places where that water accumulates. So just tremendous intensity of extreme precipitation. Some of these events we're seeing this summer amid record warm temperatures. Again, that's not a coincidence, but there is a causal influence there. Jack Lee asks, is the Omega block pattern, this is what's going on in the southern Mediterranean and over Greece, causing the stuck jet stream, or is it a symptom of the stuck jet stream? Well, it's the, literally the chicken or the egg problem, I guess. It's either or in both, in a certain sense. The reason, like, an Omega block essentially occurs when the jet stream is maybe a little bit weaker than it normally would be, and where it tends to take large latitudinal excursions. So, in this horseshoe pattern, you can kind of trace to a certain extent the jet stream is almost taking, that horseshoe pattern. But the reason why you tend to get these blocks in the first place is because the jet stream has to be in a particular configuration that favors it, which generally means the jet stream has to be sufficiently weak. And once these blocks develop, they can be pretty persistent. So they develop a little bit of their own inertia, if you will. Inertia is somewhat literally, but also there's other things going on that tend to reinforce these patterns. But once they're there, once they get stuck in place, they're pretty hard to dislodge. That tends to be a characteristic of blocks, particularly when they're anchored over a continental zone. So there can be some self-reinforcing feedbacks with the extreme heat over the continents, which is happening right now in parts of southern Europe. And so, is it a cause of the jet stream doing weird things, or is it because the jet stream is doing weird things? The answer is kind of yes and. It's both to different degrees. So, it is a manifestation of a loopy jet stream, but it's also potentially caused by a jet stream that is somewhat weaker and loopier than it would normally be in that part of the world. Let's see here. Okay, a lot of comments about no connection drops this time, which is really good to hear. So now all I gotta figure out is why my camera is doing something weird with these. I don't know if it's the camera, if there's any signals interpretation experts. Maybe it's the cable. Maybe it's, somebody even told me it might be interference with the frequency of light pulses from my LED light that I'm using to light my face in the foreground off camera. So ideas are welcome. More suggestions of no interruptions, so that is good to hear. Question from Bob Hendricks. Is it possible that this extreme weather will settle down if the rate of temperature change slows down and we reach a new homeostasis normal? Well, no, not really, because what's happening right now is not because of the rate of change, which has not really accelerated. The Earth is warming at roughly the same pace it was a decade or two ago. The problem is we're just starting to see the effects of that more viscerally, and there is an acceleration in the hydrologic cycle, for example, with rising temperature. So just every increment of a degree of warming brings about a larger relative increase in the intensification of the hydrologic cycle. It's because that water vapor holding capacity of the atmosphere rises exponentially in a warming climate. So you could reframe this slightly for somewhat better news, which is to say that if we actually stop the warming, then we do stop the increases in extreme weather events, and we kind of have to get used to whatever we've got at the point where we stabilize that warming. But slowing down the rate of warming is not enough, because the rate of warming in itself is not the problem. Slowing down the rate of warming would be a good sign that we're on our way to halting the warming, and therefore halting the increase in extreme events. But we're not seeing more extreme events because the climate is changing so quickly, but we're seeing more extreme events primarily because the climate is just warmer than it was. A warmer climate brings about a more intense hydrologic cycle. It brings about more extreme heat waves. And at some point, it might trigger some other things that start to further accentuate extremes. But for now, those are the two main things that are happening, and it's related more to the total amount of warming cumulatively rather than the rate at which the warming is occurring, which, again, the rate at which the warming is occurring hasn't really changed over time. It's a pretty constant upward trend, except that some of these impacts have clearly become more pronounced. And I think it's fair to say that the hydrologic cycle-related impacts have accelerated. So where does that leave us? It leaves us in this uncomfortable space, I think, where we know ultimately the solution is to slow and then halt. And then halt is being the operative term there. The warming, slowing it is good as a good step, intermediate step, but ultimately it does not solve the problem. We need to bring the overall amount of warming to essentially to zero. Let's see here. More good news about the connection, just issues with the visual artifacts on screen. Again, had to trade one problem for the other, I would make that trade. I'll still work on it. More questions here. That was a good question from Seth about whether this year, this crazy summer we've just seen, is it really consistent with 1.5 C of global warming? So is this essentially a representative year of 1.5 C of warming, or is the El Nino phenomenon making the extreme weather more peaky than a typical circa 2045 global warming scenario? I think we're probably going to get to 1.5 before 2045, but that aside, I think that That's a fair question. It kind of depends where you are. It kind of depends where you are. So in the tropics, for example, this year is definitely more extreme because of El Nino. But in the exotropics, which is really what we've mostly been talking about, so these extraordinary heat extremes in North America and Europe, and precipitation extremes in North America and Europe and Asia, not necessarily. This probably is more or less what a typical summer might look like at 1.5 degrees of warming in the northern hemisphere, mid latitudes, because it's not really clear that El Nino is responsible for much of what's going on in those locations right now. El Nino actually has more of an effect at mid latitudes in winter than it does in summer. It affects the tropics profoundly at all times of year. So for better or for worse, I do think this is sort of what we should expect the world to look like in summer at 1.5 degrees C. Obviously, there's still variability around that. We could have a La Nina year at 1.5 degrees C, and it will be, it'll look different. But imagine a strong El Nino event during, at 1.5 C. That year will look more like a 1.7 degree year temporarily. So that's sort of how I think about that. Just continuing to read the last of the questions here before I wrap up. Follow-up question from M. Sargent. Are you saying that the heat in the atmosphere and ocean won't be reduced by reducing carbon? Here is where the mathematical terminology becomes important. By reducing carbon emissions alone, no, it won't be, because we could reduce carbon emissions by half and we'd still be adding net warming to the planet. So we are emitting. You can kind of think of it as it's a stock and flow problem, which is a technical way of saying, think of it like a bathtub. The problem is that the bathtub, think of it as the overall pool of carbon in the Earth system, shared by the atmosphere, the ocean, the biosphere, wherever. It's in all of those. By reducing emissions, we are reducing the rate at which the tap is adding new water to the tub. That's great, but unless we have a bigger drain at the bottom than we have a tap at the top, then the level of water in the tub is going to continue to rise. So imagine, first of all, you start with an empty tub with the drain partly open. If you add water slowly from the tap, the water is going to be able to drain out at roughly the same rate that it's coming in from the tap. That is the way that the carbon cycle works in equilibrium on the Earth. So there's always carbon being added to by various sources and then being sequestered or absorbed by various sinks. So literally the equivalent of the drain being able to essentially move the same amount of water out of the tub as you're adding from the tap. But then humans came along and started to radically ramp up the amount of water coming out of the tap. So we're pulling more and more on that tap in the tub, and the drain at the bottom of the tub is remaining essentially the same. In some ways, it may be even indirectly because of things we're doing. The drain at the bottom may be shrinking slightly, but for the purposes of this visual metaphor, let's just say that the drain stays the same over time. It can drain a fixed amount of water per time, but the spigot that's letting new water into the tub we're pulling it further and further. It's adding more and more water to the tub. So the water level in the tub, what's going to happen? It's going to rise because there's more flowing in than is flowing out of the tub. And so if we just have a fire hose of water coming into the tub, which is pretty much what we have right now with our carbon emissions globally, it's not enough to start gradually, incrementally ratcheting down the flow from the fire hose. So we can start to slowly push the valve on the hose closer and closer towards closed, but for as long as the flow out of the hose exceeds the capacity of the drain to drain the tub, the water level in the tub is going to continue to rise. And that's the direct analogy with the amount of carbon in the atmosphere, which is continuing to rise, even if we stabilize our emissions, even if we decrease our emissions. Even 50% decline in emissions would be so far out of equilibrium, it would be the equivalent of taking the fire hose and only turning it halfway off. Chances are the drain at the bottom of the tubs, it can't accommodate half a fire hose worth of water. And so we'll still continue to see additional warming in all of the ocean and atmosphere systems until we essentially bring our own carbon emissions into equilibrium with the drain, which is pretty close to net zero. So we more or less have to zero out our carbon emissions, not just flatline them, not just decrease them, but we have to largely eliminate them in the long run to actually solve the problem of global warming. So think of the atmosphere's the carbon in the atmosphere as the amount of water in a bathtub, and the natural carbon sinks are the drain at the bottom of the tub, and the human source, the emission of greenhouse gases by any number of means, is the spigot at the top of the tub. We really need to turn that spigot off, not just gradually push it so that it's slightly more closed. Hopefully that makes sense and isn't too alarming of a metaphor. All right. Well, I think I'm going to leave it at that today with that bathtub metaphor. Thanks for joining. Thanks for sticking with me. I'm very glad that the stream quality now finally seems to be significantly improved. One bonus is that one of the settings that I've changed should allow for automatic closed captioning. So for those who were asking, I think I figured out why that wasn't showing up. Aside from these weird visual flashes, which again is different from the stream stalling, I'm fairly pleased with the way this has gone compared to recent streams. So if you have, if you have advice on those flashes, or if you did actually experience stalls of the stream, not just those weird visual flashes, but if I cut out or you got the spinny wheel or something like that, let me know. But otherwise, advice on the visual artifacts is appreciated, but aside from that, I think we've reached, speaking of equilibrium, I think we've reached a new one on these streams in our new home, so hopefully this connection will work out better. I'll work on the sound stuff. That's just, I gotta put some foam up on the walls. The dog bed in the corner is doing a lion's share of the sound absorbing right now, so I gotta do something a little bit more substantial than that. But thanks for joining. I'm gonna try and get back on a semi-regular schedule. And yes, appreciate the continued engagement. Great questions as always, and see you next week.